Alright, here's our last example in this section of work. And I took the liberty of drawing the open or this piece of cardboard before starting the video, because it takes me so long to try and draw something that it would have made the video an extra 5 minutes longer. Okay, an open box with a rectangular base is to be constructed from a rectangular piece of cardboard, 16 centimeters wide and 21 centimeters long, by cutting a square from each corner and then bending up the sides. Find the size of the corner square that will produce a box having the largest possible volume. So those are our two key words in this question. Alright, so here's my piece of paper, my cardboard. It's 21 centimeters long and 16 centimeters wide, and I'm going to cut a square from each corner. Square implies the side lengths are the same length. I'm going to cut out these 4 squares. Okay, and then I'm going to fold up the sides, and that's going to give me an open box. Alright, now if I make my square's side lengths all x, when I fold up my box, that will actually be the height of my box. So let's let x be the height of the box in centimeters. So immediately you can see that I'm relating this square that I'm cutting out of the corners to something on my box that I'm folding. Okay. And we also need to think about a reasonable domain for the size of squares. So if I have a look here, I can keep on making these squares larger and larger and larger, but at some point I can no longer create any more squares because they kind of meet up. So a reasonable domain for this question would be x must be greater than or equal to 0, but less than or equal to 8 centimeters. Okay. So let's see, we're wanting the largest possible volume. How do we find the volume of a box? Well, we know that volume is length times width times height. And the length of our box has to be 21 minus that x and minus that x on this side too. Remember, I've got an x here, so we've got 21 minus 2x. Our width would be 16 minus 2x, and our height is just x. Alright, and now we're going to expand that. So I'm going to do FOIL first and then multiply it all by x. So I get 336 minus 42x minus 32x plus 4x squared, and we're multiplying that by x, and that gives us our volume, which is 4x cubed minus 74x squared plus 336x. Alright, now we're wanting to maximize our volume. So we know that our maximums or minimums are going to occur at our stationary points, and that is when our derivative, our first derivative, is equal to 0. So to maximize our volume, our mins or maxes occur at v dashed of x equal to 0. Alright, so let's find our derivative. So v dashed of x is going to have to be 12x squared minus 148x plus 336, and we need to put that equal to 0. So 12x squared plus 148x plus 336 equals 0. 4 goes into all of those, so we have that 3x squared minus 37x plus 84 equals 0, and We can factorize that to 3x minus 28 and x minus 3 using our null factor law. X will be 28 on 3 centimeters, or x equals 3 centimeters. Now, we need to look at these two answers and decide whether they are firstly both valid. If they are both valid, we then need to confirm which one is the maximum and which is the minimum. All right. So 28 on 3 works out to 9 1/3, and that's outside of our domain, so we can just discard that. And we can say, because we know that x has to be between 0 and 8. Okay, I'm just going to go through confirming the nature using our second derivative test. Okay, so these are always the steps we go through. Okay, so we're always going to confirm our nature, and we will always check our global maxes and mins as well. Okay, so our second derivative is 24x minus 148, and that when x equals 3 is 24 times 3 minus 148. That's negative 76, and that's what we want, because if it's negative, it means it is concave down. Therefore, it is a local maximum. All right. Now, our domain goes from 0 to 8, so we can just confirm our global maxes and mins. Global max and min. So v at 0 is going to be 0, and v of 8 is going to be 0. So therefore, x equals 3 gives a maximum volume, and usually they'll ask you to tell them what the volume is. So we would say our volume is 450 cubic centimeters. So therefore, the maximum volume is 450 cubic centimeters when x equals 3 centimeters.